Hello, my name is Richard Droste, and I will be presenting our paper, Automatic Probe Movement Guidance for Freehand Obstetric Ultrasound. First, some background. Ultrasound scanning is an indispensable tool in obstetrics, since it is safe, real-time, and low-cost, and it aids in the early detection of fetal abnormalities. It follows a standardized protocol, with scans in the first, second, and third trimester of pregnancy. Sonographers acquire biometric standard planes in order to detect growth restrictions. According to the UK protocol, this is what the biometric standard planes look like: abdominal standard plane, femur standard plane, and transventricular plane. This is what the images in the second and third trimester typically look like. And this is what the clinical acquisition setup looks like. A sonographer is looking at the screen of the ultrasound scanner and is manipulating the probe until they have achieved the desired appearance. The problem that we are facing is that acquiring standard planes is difficult, and therefore often the limiting factor in deployment. The solution that we propose is an automatic probe movement guidance system that is learned from recorded clinical acquisitions. In particular, we attach a motion sensor directly to the ultrasound probe. Then we take the ultrasound video signal and the probe motion signal and feed it into a network that we term US-GuideNet, which in turn outputs the probe movement guidance signal. Now, how do we pose this problem formally? Let's have a look at a standard plane acquisition sequence up to a video frame XT. In addition, we define the standard plane as XS. We represent the probe rotation between any video frame XT1 and XT2 with a quaternion, since representing rotations as quaternions has many advantages over angle-based representations like Euler angle, such as the fact that they can be smoothly interpolated and don't have any discontinuities. Next, we can compute the quaternion rotations between the probe orientation at each acquisition video frame and the rotations of the probe between each video frame and the desired standard plane. We pose the probe movement guidance problem as a behavioral cloning problem, which is a type of imitation learning. We take a policy network pi theta, which receives the probe rotation at each video frame and the video frame as inputs. In addition, we introduce a hidden state that is passed from time step to time step in order to capture temporal information. This means that we can represent the state of the system with a tuple of the current video frame, the current rotation, and the hidden state. For goal prediction, we have the policy network predict the probe rotation from the current video frame XT to the desired standard plane position. This means the network is essentially guessing the position of the standard plane, and this can be turned into a real-time guidance signal. We also explore an additional formulation, which we term action prediction, where the policy network instead predicts the next probe rotation that the sonographer would perform at the current time step. Next, let's have a closer look at the policy network US-GuideNet. As mentioned before, we can represent the state at time t with the tuple of the current video frame, the current probe rotation, and the hidden state. First, we process the image with a lightweight MobileNet V2 CNN, which can run in real time on a CPU. Next, we perform a custom concat-poo operation on the MobileNet V2 features, which extracts global information via global average pooling and spatial information via the x and y coordinates of the center of mass. We introduce an auxiliary loss, which regresses the SonoNet class probabilities from the global average pool features, where the SonoNet is a previously proposed network that can classify ultrasound images. Next, the concatenated features are reduced in dimensionality with a fully connected layer and concatenated with the current probe rotation. Then we update the hidden state with a gated recurrent unit, which is a type of recurrent neural network, and pass the GRU output through another fully connected layer that regresses the goal prediction or the action prediction. Now, how do we train this network? we propose a loss function which consists of 3 parts. First, we have the similarity loss, which maximizes the cosine similarity between the predicted probe rotation and the true observed probe rotation. Next, we have the norm loss, which keeps the norm of the predicted quaternion close to 1, which is necessary for valid rotation quaternions. Finally, we have the aforementioned auxiliary loss, which is a weighted cross entropy between the auxiliary softmax output and the SONONET class probabilities with a weight vector W that balances the SONONET classes. Finally, we simply sum the loss components from a start frame T0 to an end frame capital T with a warm-up term W and empirical weighting factors alpha and beta. Regarding the data, this project is part of the PULSE project, which acquires a dataset of full-length routine clinical ultrasound scans, where the video is recorded lossless at 30 Hz, and the motion of all probes is recorded with commodity IMUs. Here we use a subset that consists of 464 second and third trimester ultrasound scans acquired by 17 sonographers, which results in over 5,000 Cineplane acquisitions. For training, we propose a 3-step procedure where first the CNN is trained with the auxiliary loss only. Next, the entire network is trained with all Cineplane acquisitions. And finally, the network is fine-tuned for each Cineplane type separately. Here we show qualitative results for the goal prediction output. Due to time constraints, I will not be able to discuss these in details here, but please feel free to look at the recorded presentation video and observe these in detail. Next, let's have a look at the quantitative results, which we split into the 3 Cineplane types and an average of all of them. We used a prediction accuracy metric, which simply compares the predicted probe orientation to the target orientation versus the current orientation to the target orientation. Moreover, we plot this for different angle to the target thresholds. In addition, we introduce a baseline, which is to simply follow the current probe rotation. For goal prediction, we observe that the model outperforms the baseline for all angles above 6 degrees, and we observe a generally high accuracy with over 90% for the TVP and ASP planes. Also, we observe similar results for action prediction. Now, a brief discussion of the limitations. Our network is evaluated on pre-acquired data. However, it is real-world pre-acquired clinical data, which suggests that it should transfer to a real-world deployment scenario. Also, the network output is limited to probe rotation. However, once the true orientation of the Cineplane is known, then the Cineplane acquisition problem reduces to transversing the through-plane dimension, which is a much simplified problem. So, in conclusion, we have proposed a model that provides accurate navigation signal towards biometric Cineplanes. And this is the first probe movement guidance system that is trained for freehand obstetric ultrasound scanning and is trained and evaluated with routine clinical data. Thank you very much for your attention.